Hi, we are the legendary Rover team from Rzeszów University of Technology, Poland. Our team consists of approximately 70 students from various departments: mechanics, electronics and software, science, IT, marketing, drones, and finance. This year, we're pleased to present our new rover, legendary 3.0 Kamakiri. Thanks to the kindness of Poznań University of Technology, we were able to test the rover and record several scenes at the Poznań University of Technology's new campus, which is part of the European Space Agency, ESA Spaceship Poland, and ESA Phylab Poland initiatives in Konkolewo. We hope you enjoy it. This framework provides real-time communication and significantly simplifies the process of autonomous rover control via packages and tools supporting sensors, 3D cameras, and route planning systems. Manipulator control using inverse kinematics is also implemented using ROS2. ROS2 commands are sent via a Wi-Fi access point located on the mast. Currently, we only use the 2.4 GHz band and radio module satellites in the 433 MHz band. A new 5 GHz and 2.4 GHz Wi-Fi system is currently being tested. The mechanical architecture of our rover is structurally divided into the robotic arm, frame, and drivetrain assembly. The frame is welded out of 15 by 15 and 12 by 12 mm aluminum profiles to ensure a rigid base for other modules, with mass of 1.8 kg only. A foldable mast placed on the back of the rover utilizes a place for antennas and 360 degrees camera. Mobility of the rover is ensured by a four-wheel rocker suspension system. BLDC motor reducers connected with 3D printed elastic wheels give a decent traction on tough terrain. Turning is powered by stepper motors with planetary reducers to ensure precision and sufficient power. Variable types of steering let operators to precisely maneuver during tasks. For control, each of the four wheels boxes contains BLDC motor controllers, stepper motor controllers, an encoder reading system, a step-down converter powering the driving logic, and an STM F446 array control microprocessor. Electronic components are enclosed in 3D printed modular boxes to protect them from environmental conditions. The system includes a main computer, a galvanically protected power supply with 12 high current outputs, and a highly adaptable multifunction block that controls various actuators dynamically, depending on the mission's characteristics. The rover's autonomy architecture is based on ROS2 Humble, running on a Geekom microcomputer which handles system synchronization. Localization is managed by an extended Kalman filter that fuses data from four sources: wheel odometry, IMU readings, visual odometry, and RTK GPS. This achieves a positioning accuracy of several dozen centimeters. For 3D mapping and spatial perception, the system uses an Intel RealSense D455F camera. The integrated IR pass filter mitigates solar glare, enabling accurate point cloud generation in direct sunlight from motion planning. A camera-driven 3D obstacle avoidance system is currently under development. Object detection is processed through OpenCV and a custom YOLO model to autonomously identify specific targets, including Aruko markers, an orange hammer, and various bottles. The drilling system reaches a minimum depth of 10 cm. Once the target depth is achieved, integrated probes are deployed to measure soil moisture and temperature. Extracted samples are transported into hermetically sealed containers to prevent cross-contamination. Simultaneously, we monitor the concentration of metabolic gases to identify potential biological signals. On-board biochemical tests utilize specialized reagents to detect proteins. Finally, the rover fuses GNSS and Geiger data to generate a spatial radiation map. To perform tasks during competition, our rover currently utilizes a proven robotic arm combined with a reliable gripper. The submodule that controls the older manipulators contain dedicated DC motor drivers, allowing operators to efficiently manipulate objects in the field. However, we are also developing a new, highly complex 6 degrees of freedom robotic arm with aluminum construction and high-precision harmonic drives, designed to lift up to 6 kg and reach 1.2 meters. It is currently in the testing and integration phase. For this new system, electronics are built directly into each joint and controlled via the CAN interface. We will achieve its full operational capability soon.